So interestingly, in this formulation, to get the circulatory lift, all what you need to get is the average of the downwash. This is one thing. Okay? But now if you compare this circulatory lift to the circulation, they are not the same anymore. If you look here, it's B naught B1 over 2 minus lambda naught, but we have lambda 1 extra. We have lambda 1 extra. So what is this lambda 1? What is this lambda 1? Why it makes things so different? First of all, it's clear that the circulatory lift is not rho u gamma b, right? Because they are different. Here is the circulatory lift, it's angle of attack 3/4 minus downwash due to wake. If there is no wake, it's a steady problem. This is 0 and both lambdas are 0, they are exactly the same. But if not, then this guy, you need to add to it lambda 1. Okay? So let's see, like we said, the problem is not complete. This is waiting, and we need another key equation. So I'll try to get to you, with you now, the key equation of Peters. Also to identify why lambda 1 makes things problematic.
So,
yes?
why not adding lambda 1 and subtracting?
That's right, yeah, you can do that. So, what do you mean? You can add here lambda 1 over 2, right? Or negative lambda 1 over 2.
Yeah.
So you get the left to gamma plus whatever, lambda 1 over 2, right?
Yes, yeah. So then the
And then
circulatory
you will
lift.
have to take lambda 1 with here, but this is not, yeah, this is what we're saying, is that this is not the common definition. When people say circulatory lift, unfortunately they mean this. So it's an arbitrary definition. So in the common definition of circulatory lift is not lifted into circulation. This is lifted into circulation. This is the circulation just multiplied by constant to get the lifted into circulation. They are not the same. Let's skip this. We had the pressure term before. Where is the pressure term? Yeah, this equation. This equation is good. We want to do here. Let's differentiate this equation with respect to x, partial x, which we wanted to do before. So you get u partial x gamma plus this guy goes away, and here if you apply, like I said, if you apply the Leibniz, you get this evaluated in the upper limit. So you get partial t for gamma wake. Very nice equation. I'll just copy it there. U partial x gamma wake of x and t plus partial t gamma wake of x and t is 0. This looks like d gamma by dt total derivative is 0, and that's correct. This is the 2D equation of vorticity equation. The vorticity equation in two-dimensional is d by dt for the vorticity equals 0 for an inviscid flow. So you just recover it here from the pressure equation that we got. So anyway, from this equation, and the definition of lambda, here is the definition of lambda. What's the definition of lambda? It's 1 over 2 pi. It's the downwash due to this gamma wake, d zeta over x minus zeta. So this is at x and t, lambda of x and t. Okay? So if you use these two, this guy, and here's the definition. So let's compute u partial lambda partial x plus partial lambda partial t and make use of this guy. You will find this. So just do it on your base. I will not waste time here. It's very straightforward, nothing fancy at all. This will give you 1 over 2 pi gamma pound dot over b minus x. So this is the key relation. Why? Let's see why this is the key relation. Here this is lambdas, so this is the lambda coefficient, lambda naught and lambda n. And And here partial t, so I have lambda dot naught lambda n dot. And here this is gamma b. Gamma b, here is gamma b. So the dot has these four coefficient dots only. B naught 1 lambda naught lambda 1 dot. So when you do this equation, you can apply this equation. When you do this equation, I'm sorry, and you do the expansion, so the lambda in terms of lambda naught lambda n and the same here, and equate coefficients, you get infinite number of equations, right? You equate the coefficient of the free term, the coefficient of cosine phi, cosine 2 phi, and so on and so on. So you get infinite number of equations. The b's are known, and these equations gives you ordinary differential equations in lambdas, right? You can see it right away. So you get lambda dot in terms of lambda, which is not a mu unknown, and the b's, which are known. So these are differential equations in lambdas. So this is what Peters called the finite state. Well, you get infinite of these, and you truncate after some number. So say I will take 8 lambdas. So you get the first equation in the first 8 lambdas and ignore all the rest of the lambdas. So this is an approximation for the PDE system into a number of ODEs. 2 lectures ago, we already wrote a state space model. Remember, this is the differential equation, and this is linear. You can write it as a state space model. Here you can write it as a state space model. You can write it as lambda dot equals exactly like this, and you can go to his paper, you will find what A looks like. I do not waste some time to derive it. Plus B times your inputs, which is the B dots. So this is a state space model, okay? And we derived the state space model 2 lectures ago. There was only 2 states. Here he needed 8 states to get good results. So this is a drawback. But in our state space model, the x's, the states, they didn't have any meaning whatsoever. Any meaning whatsoever. But here, the states are, these are lambda n's. Okay? The states are the downwash due to weight. So at least they have physical meaning. So this is a big plus for his model. Okay, I think maybe if I take just a couple minutes, I'll show you the last piece. Okay, so the circulatory lift, which is, where is the circulatory lift? It's this guy. So it's 2 pi B naught plus B1 over 2. These coefficients are the motion, angle of attack 3/4 minus lambda naught. If we divide it by quasi-steady to get the transfer function of the flow, let's divide by quasi-steady. What's the quasi-steady? If this is the circulatory list, can you tell me what's the quasi-steady? What's the quasi-steady from here? Yeah, this is so this is 2 pi B naught plus B1 over 2. And he was clever enough to write it in terms, just give me this couple of minutes and I'll finish. To write it in terms of gamma. So just recall, we wrote gamma before already. It was something like 2 pi UB B naught plus B1 over 2 minus lambda naught plus lambda 1 over 2. So let's call this gamma hat as non-dimensional and divide by these guys. So this is, first of all, 2 pi goes away, and these guys are the first 3 terms here. So this is gamma plus lambda 1 over 2 divided by gamma plus lambda naught plus lambda 1 over 2. If we divide up and down by gamma hat, so this is 1 plus lambda 1 over 2 divided by lambda naught plus 1 lambda 1 over 2. Lambda 1 over 2 gamma, right? Lambda 1 over 2 gamma. So the transfer function of our lift dynamics can be determined right away very easily if you have these two transfer functions, right? If you give me these two transfer functions, I will get you the transfer function of the lift dynamics, which we spent 3 days derived by Tudorson, right? So let's get how we can get like this. Step gamma. Remember, gamma is not gamma quasi-steady. It's not a quasi-steady circulation, because quasi-steady means airfoil motion. This is what we use too. Gamma here is the actual circulation, right? Gamma is the actual circulation. So step gamma doesn't mean step angle of attack. Step gamma here doesn't mean step angle of attack. It's not step in quasi-steady circulation. It's step in circulation. So it's as if you have an airfoil like this, and all of a sudden you have gamma. What does happen? And what do I need? What do I need? I need these two transfer functions only. What's that? I need the downwash due to the weight, due to a step gamma. This is very easy. Why? Because if I have a step gamma here, the weight is also like this, right? It's the exact same amount of gamma, and it travels, I know this distance. If you have just